You are more than welcome to go to the top here and to go to this YouTube video. It's less than 4 minutes long, and it talks about where you see E in real life. Now, you have not learned about E up to this point. In each of my classes up to third period, when I've asked how many of you have heard about the number E, generally a few people have raised your hand. So on the number line, we often focus on integers, right? And, oops, there's an integer that lies right here that's irrational, and it's actually the number E. It's the number E. E is referred to as Euler's number. A mathematician named Euler discovered that in real life that we often model science and quantities in science that grow and decay continuously with this number. And so if you watch that video, they would show you different parts in science and different real life examples of where that happens. So Euler's number is used extensively in science to model quantities that grow and decay continuously. So in fact, if you ask somebody outside of a math classroom, when you solve things, what is the most common base that you use? What is the most common base you use in real life when we actually have to use this? It is the number E, okay? So it's the most common base of a log that we use, because it relates and models real life applicational problems. All right, so we're going to graph what is referred to as the natural base exponential function. This is the natural base exponential function. Remember that E is a number. It's a positive number. So if you take a positive number greater than 1, and this is a positive number greater than 1, and you raise it to the x power, is that going to represent exponential growth or decay? You should know this better. If you take a number that's greater than 1 and you raise it to an x, is that an example of exponential growth or decay? So turn to your partner. What does that look like? Does it rise up to the left or up to the right? So we know it's something like this, right? Okay. So I'm going to go through this again because I had computer problems. We're going to kind of speed through this lesson. This is my basic equation. If I plug in 0, remember any number raised to the 0 power gives you an answer of 1. So 0, 1 is my first point. 0, 1. I plugged in 0, and I know any number to the 0 is 1. The next number I'm going to plug in is 1. So e to the first, well, 3 to the first is 3. 4 to the first is 4. So e to the first is just the quantity of e. What is e? E is approximately, it's an irrational number, it's approximately 2.718. And of course it goes on and on and on. It's irrational, doesn't have any patterns. So I went over 1. That's my input value. And the x point value is approximately, again, 2.718. So we can see that this is an example of an exponential function. Bless you. So 2 things I want you to take away from part 1 of your notes. This is called the natural base exponential function. The number e has approximately this value, and in Euler's number is what it's called. And even some scientists call it a magical number because it occurs so often in math and real life application problems. And it's extensively used to model science problems. Okay, part 2, and we have 2 other parts that are like part 2 today. I call these mindless problems. It's like when you plug something into your calculator, you don't have to do any work and it just gives you an answer. On your calculator, you're going to see that e to the x is in blue. So to get there, once we turn on the calculator, you're going to hit second and then e. And what we're doing right now is we're just going, how do you evaluate an expression that has e? So here's e. Let's go e to the 4th. We're going to round it to the nearest thousandths. So to represent rounding, you use the approximation symbol, 54.598. Okay, we already did this one. E to the first. So if my input value is 1, what is my output value? 2.718. We've already done this one. If my input value is 0, what's the output value? Now how this is different than A or C is that you're not rounding. So we're going to put equals 1. And let's do the last one together. Second, and then e to the x. This time we're typing in negative 1.3. And we're going to approximate it. Approximately 0.273. What is the relationship between the natural base exponential function? Boy, that's wordy. Underline this and write y equals e to the x. And a logarithmic function, so y equals log base, and it says a logarithmic function that has a natural log. Remember, e is the natural base. Now, before we even describe or figure out what is the relationship, you have to know that there is an equivalent form of this. It's y equals ln of x. It's called the natural log base. Now, I have never understood why natural log, if we were going to represent, would be NL, right? Natural log. For some reason, it is switched, and so it is ln, but this means the natural log. These are equivalent forms. So what is the relationship? Make yourself a graph. And what we're going to see is if I asked you for inverse operations, the opposite or the inverse operation of adding is subtracting, and the inverse operation of multiplying is, okay? What you're going to learn is that the inverse operation of e to the x is either one of these. They're inverse. And earlier this year when we started learning about inverses, we learned that if two functions were inverses of one another, they would reflect across the line y equals x. We also learned that their ordered pairs would simply be flipped. So I'm going to look up above to part 1 in your notes, and I'm going to graph the natural log exponential function. So 0, 1, and 1, and 2.718. Okay. I'll give you one more second to do that. Then I want you to show you how this works. So I want you to go to do second plus 712, please. And if you look on your calculator, I told you these are equivalent. Do you see a log base e? And some students in previous hours are like, yeah, I do. I see it. It's right here. But what's interesting about this is not a log base e. What is it actually? Log base 10. It's a common log. This is your log base e, your ln button. So go to y equals and go ln of x. So we know it's a log function. In this unit, we already learned what log functions look like. And what I want to do is I want to see, and I know that I approximated this, so it's not going to be exact. I want to see, are these inverses? So if it is 0, 1, then I know a point on this function. 1 second, this is y equals e to the x. I know a point on the next function, the ln of x, will be 1, 0. So let's check. I have this graph out. Do second trace value. If we input 1, we should get an output value of 0. Is that true? Okay, now I know this is going to be slightly off because I had to round this. Do second trace, and now I'm going to flip this ordered pair. But remember, I had to round here. So now we're going to go 2.718. It should be really close to 1. Why is it not exactly 1? Because this was irrational and I rounded it. Is that really close to 1? So I'm going to go over 2.78 and up 1, and then I'm going to draw this graph. And if I would have been a little more precise in graphing the two functions, you'd be able to see that they actually reflect across this line and that their ordered pairs are simply flipped. So they are inverses of one another. They are inverses. So let's write that down. Y equals the ln of x, which also can be written as y equals log base e of x, is the inverse of y equals e to the x power. Okay, we're going to go back to this mindless work just like number 2. How do we evaluate these ln's? So let's go press clear. Find the ln button, the natural log. So the natural log of 4, it is irrational, so we'll round it to the nearest thousandths. It is approximately 1.386. With your partner, please do B at the same time I'm doing it. Go ahead. I know this sounds silly, but for next year, will teach this in the reverse order. So I'm going to have you flip over, and we're going to go through 6 and then go back to 5 afterwards. And I think that your understanding of the concepts will be greater. In this problem, you are asked to evaluate the expressions using the inverse properties of base e and logarithms. And really what we're doing is we're going back to what you already know. Let's rewrite this. Instead of saying ln, you should know that ln is the same as log base e. Previously in this unit, we learned that when the base is the same as the base of the log in the exponent position, this cancels out, and this answer is 7. Going on to number 8, let's rewrite ln as log base e because they're equivalent. Again, you have learned that log base e followed by e we can cancel these out because they have the same base, and the number following the base is the same, and we bring down 4x plus 3. Does anybody have questions for me about A or B of number 6? Flip over and find 5. The key is they don't want you to solve that. They're leading up to that in number 7, part 7 of your notes. Here they just want us to rewrite it in our opposite forms, which is going to lead to us solving it. So this is an exponential form. What is the inverse of exponential? You just learned that today. Logarithmic, right? And this is logarithmic, so the inverse is exponential with an e. Okay, so here we go. So this problem, part A, I want you to look back here. This problem right here relates to this problem. And you're like, I don't understand how they relate. Do you see how this number is the same as this number? And we cancel them out. Does everybody see that? Okay. So I want to write something in front of this so that the e's cancel and x comes down, because that's my whole goal, is to isolate the x. What could I write in front of this e so that the e will cancel? Log base e, right? And remember, whatever you do to one side, you must also do to the opposite side. So I'm going to write that in a different colored writing utensil. And then I'm going to write what already existed in this problem. Not required to write in 2 different color writing utensils. I just think it shows up better. Okay, so now that I have done this, as long as I did it to both sides, the equation is still balanced. The log base e and the e cancel, and I get to bring down the x. What I want you to recognize is that we can write this in a different form that's equivalent. Log base e is the same as ln. We started in an exponential form, natural base exponential function, and we got an answer that's in logarithmic natural base. Okay, now we start with natural base. We're doing the opposite. So let's rewrite this as log base e. Flip to the back and find number 6, part A. Find number 6, part A. Flip to the back, find number 6, part A. What can I do to this problem to eliminate the log base e? Write it e as the base on both sides. Thank you. That's what I'm adding to this problem. And what already existed now becomes the exponent on both sides. Okay, the log base e on top and the e down below cancel, and I bring down the x. Remember, you're not asked in this part to solve, just to rewrite it. So rewrite it from exponential to logarithmic or logarithmic to exponential. Let's check again. We started in exponential with the natural base. We ended in logarithmic with natural base. We started with logarithmic natural base. We ended with exponential natural base. Flip over. The whole goal of today is to understand how to do problems like 7 and 9. And that will lead us into doing problem 8 tomorrow. Tomorrow 8 is all word problems. So number 7, our goal is to solve for e. So on the side that contains the e, what number is furthest from the e and not touching? It is the 7. The opposite operation would be to add 7. You do not want to round until the very last step. If you round multiple times, you get really an error in your final answer, because the more times you round, the less accurate your final answer is. So now to get rid of this 5, we're going to do the opposite operation, which is dividing by 5. Okay, this goes back to what we've just learned. What can I write in front of this function that would allow me to cancel out the e? So log base e, good. Log base e to both sides. And I'll write down what was already there. On the left-hand side, the log base e's cancel, and I get to bring down the negative x. On the right, I have log base e of 9/5. Your last step is to simply get rid of the negative sign, which would be divide by -1. So I'm going to put this in brackets here, and my last step would be to divide by -1. So how do we do this on a graphing calculator? Please press clear. Recognize that log base e is not the same as the common log, which you see here. So we're going to hit ln, because the natural log, or ln key, is the same as log base e. 9 divided by 5 in parentheses, press enter. And when we take it, or divide it by the negative 1, we're just going to switch the sign. And let's round it to the nearest thousandths. Part B is very similar. So part B, our first step will be to subtract 3. It's on the side that contains Euler's number, and it's not touching the e. Again, how can we remove the e? What operation can we do? Log base e to both sides. I'm going to write down what already existed. Then on the side that contains Euler's number, we can see that log base e and e cancel, and you bring down the -2. Recall that log base e is really the natural log. So ln of 5, I'm going to put it in parentheses because I recognize the last step is going to be to divide by -2. On the calculator, let's go ln of 5. Get an answer and divide it by -2. And now round it to the nearest thousandths. We're going to skip 8 and we're going to come back to it tomorrow. That's how we are going to start. Class tomorrow is with number 8. Let's go down to number 9. How can I rewrite ln? What's an equivalent form? Log base e of 5x equals 4. Now there's multiple ways to solve this, by the way. It's not just always, and still continue with the math rules. So one way is I can now create a base e on both sides, and as long as I do it to both sides, I'm okay. I haven't broken any math rules. The e and the log base e cancel, and I bring down the 5x. And my final step to isolate the x would be to divide both sides by 5. So on your calculator, as a reminder, how do you find that e? It's going to be second ln, so e to the 4th enter, and divide it by 5. Okay, now this was tricky for students in previous hours to round to the nearest thousandths. So I go 3 places over, which is a 9, and I look at the number behind it. Because it's greater than 5, it will bump the 9, which looks like a 19, actually up to a 20. X is approximately 10.920. Okay, and our last one over here involves an inequality. Let's rewrite ln as log base e. And just like we did the previous problems, I can make all of this an exponent, and the base is going to be base e. Again, why am I choosing base e? Because I want the number to be the same as the base of the log. In doing so, it cancels. I bring down x plus 1. I have not divided or multiplied by negative, so I don't need to worry about at this point flipping the inequality symbol. My last step will be to subtract 1 from both sides. So find the e button, raise it to the -2 power and get an answer, and then subtract 1 from that answer. So approximately, okay, I got it here. It's hard to do approximately when you have this. So let's do is greater than -0.865.